Welcome to Tech Explained. Today, we're unlocking the complexities of CCSP Domain 2, Cloud Data Security.
Mm-hmm.
This part of our journey, it's all about understanding how to truly secure your information in cloud environments.
Right.
We're going to break down the fundamental concepts, the critical strategies, and the clever technologies you need to grasp, to keep sensitive information safe and sound.
Absolutely.
Think of this as your essential guide, really, to navigating the intricate world of cloud data. We'll uncover foundational models, clarify critical roles, and explore a whole suite of techniques designed to protect data throughout its entire journey.
Yeah.
Get ready for some serious aha moments that will clarify exactly what it takes to secure cloud data effectively.
Exactly. And we'll start with those bedrock principles, the foundational ideas that everything else in cloud data security is built on.
Okay.
Then we'll move seamlessly into the practical applications and the various tools organizations deploy to maintain control and, importantly, ensure compliance over their most valuable digital assets.
Right.
Our aim is really to help you understand not just the what of data protection, but critically, the why behind each control and the how of implementing them successfully in the cloud.
All right, let's unpack this then with some core concepts. These are absolutely fundamental to data security, whether you're operating in the cloud or, frankly, anywhere else. These are like the very bedrock principles of protecting information.
The classic framework we always begin with, is the CIA Triad: confidentiality, integrity, and availability. These three pillars, they really underpin almost every security control you'll encounter.
Okay, CIA. Let's break that down.
So confidentiality. It's all about secrecy.
Secrecy.
Yeah, keeping data hidden from anyone who is not authorized to see it. Imagine a highly sensitive business plan or customer financial record.
Right, critical stuff.
Exactly. If these fall into the wrong hands or are even just inadvertently exposed, that's a breach of confidentiality. The goal is simple: ensure only authorized individuals or systems have the key, so to speak, to access and read that information.
Like a locked vault.
Precisely. A classic example of a confidentiality failure. That's when, say, a company's customer database gets exposed because of a misconfigured cloud storage bucket.
Oh, yeah. Hear about that all the time.
Yeah, unfortunately. It allows unauthorized parties to just download sensitive personal data. And that's not just a technical glitch, It can lead to massive financial penalties, huge reputational damage, and a complete loss of customer trust.
Absolutely devastating. Okay, so that's confidentiality. What's the I?
The I is integrity. This pillar focuses on trustworthiness and accuracy.
Trustworthiness.
Integrity ensures that data hasn't been tampered with, corrupted, or altered in any unauthorized way. It's all about preserving the precision and reliability of your information.
So making sure the data is what it's supposed to be.
Exactly. Consider a financial transaction record. If the amount or the recipient could be changed without anyone noticing, well, the system would be useless, right? So integrity controls, things like checksums or digital signatures, they ensure that any unauthorized modification does occur. It's immediately detectable.
Okay, so you can trust the data.
You can trust it. A failure in integrity could be, say, a malicious actor changing medical records, or even just a software bug corrupting a critical configuration file. That could lead to widespread system outages or really bad business decisions based on faulty data.
Yeah, bad data leads to bad outcomes. Got it. And the A.
And finally, availability. This means ensuring that authorized users can access the data and the systems whenever and wherever they need it.
Right, it has to be there when you need it.
It has to be there. This is all about uptime and accessibility. If your e-commerce website goes down during a big sale, or your employees can't access critical customer data during business hours, well, that's a failure of availability.
And potentially a huge loss of business.
Huge loss. Availability ensures business continuity. A denial of service attack, for instance, directly targets availability, making resources inaccessible to legitimate users. Its absence can lead to lost revenue, frustrated customers, and significant operational paralysis.
So all three are critical.
Absolutely. All three elements, confidentiality, integrity, availability, must be robustly addressed for a complete security posture. A weakness in any one really undermines the others.
So if confidentiality is secrecy, integrity is accuracy, and availability is accessibility, it feels like there must be more to it. Are there other crucial properties we need to consider beyond just the triad to really secure information? Other layers, maybe?
There absolutely are, yeah. While the CIA triad is, well, foundational, we need to layer in authenticity and non-repudiation to build a truly robust security framework.
Okay, authenticity and non-repudiation. Tell me about authenticity first.
Authenticity is about verifying identity and origin.
Verifying identity.
Yeah.
Okay.
It means confirming that a person or system is genuinely who or what they claim to be. This is absolutely vital in digital interactions. For example, when you log into an application, authentication processes confirm you are truly the user you claim to be, preventing imposters.
Makes sense. Like username and password or MFA.
Exactly. And authenticity also extends to data itself, verifying that data truly originated from the claimed source and hasn't been, spoofed or faked.
Okay.
Think of receiving an email that claims to be from your CEO asking for a wire transfer.
The classic phishing attempt.
Right. Authenticity controls, maybe like digital signatures on emails, help you confirm that the message genuinely came from them and not a phisher. It builds trust in that digital interaction. Without authenticity, an attacker could impersonate a trusted entity, leading to severe compromises.
Okay, so that's verifying who or what. What about non-repudiation then?
Non-repudiation takes authenticity a step further. It prevents someone from plausibly denying they performed an action or sent a message.
So they can't say, it wasn't me.
Exactly. They can't say it wasn't me. Imagine a digital contract being signed or a critical command executed in a production system. Non-repudiation ensures that once that action is performed, the actor cannot later claim they didn't do it.
How does that work?
Well, it's often like an undeniable digital signature on a deed, or maybe a time-stamped, cryptographically sealed log entry. It creates that undeniable link.
Oh, okay.
It's crucial for accountability, for legal enforceability, and definitely for forensics in digital transactions and operations. It provides that unbreakable link between an action and the entity that performed it. It's invaluable for auditing and, legal proceedings.
Okay, data in the cloud. It involves so many moving parts, different entities. It sounds like there are clearly defined roles that dictate who is ultimately accountable for protecting the data, and then who handles the actual technical heavy lifting. How are these responsibilities usually structured, especially when you're dealing with cloud providers?
They are indeed clearly defined, and understanding them is really crucial for clarity, for effective governance, and honestly, for avoiding dangerous gaps in accountability.
Okay.
First, you have the data owner, sometimes called the data controller, especially in privacy contexts like GDPR.
Right, owner or controller.
This individual or entity holds the ultimate accountability for protecting the organization's data. They possess the legal rights to the data, and they're responsible for defining the overarching policies around its use, retention, and protection.
So high-level responsibility.
Very high level. In a cloud setting, this is typically a senior individual or department within the cloud customer organization, maybe a C-suite executive, or the head of a specific business unit that relies on that data.
Okay.
And it's absolutely vital to remember this, that ultimate accountability, it cannot be delegated. Even when you outsource services to a cloud provider, the customer always retains ownership and the ultimate legal responsibility for their data.
That's a key point. Accountability stays with the owner?
Always. Next, there's the data processor. This is the entity, most commonly the cloud provider itself, that processes data on behalf of the data owner.
Okay, so they're acting on instructions.
Exactly. Strictly according to the data owner's instructions and policies. For instance, if you migrate your customer database to a cloud provider's platform, the provider becomes the data processor. They handle the storage, the compute, the networking operations that enable your application to process that data. They execute the operational tasks.
Got it. Then who handles the tech security side?
That's typically the data custodian. These individuals have the technical responsibility for implementing and managing the security controls.
Ah, the hands-on security folks.
Exactly. They administer security configurations, ensure data availability, manage storage capacity, handle data backups, oversee restoration procedures. Their job definitely gets more complex when data moves to the cloud, especially, say, in a software as a service model.
Why SaaS specifically?
Well, in SaaS, the customer's data custodian has much less direct control over the underlying infrastructure. They're relying heavily on the cloud provider's built-in controls and APIs. So their focus shifts from direct server management to configuring the security features provided by the SaaS platform and monitoring its compliance.
Makes sense. What about a data steward? I've heard that term too.
Good one. The data steward roles focus more on data governance, data quality, and compliance, often from a business perspective.
Okay, business focus.
Right. They ensure data is in the correct format, has appropriate metadata, and can be used effectively and ethically for business purposes. They sort of bridge the gap between the technical storage and the business utility of the data, ensuring its fitness for purpose and compliance with internal and external regulations.
Can you give an example?
Sure. A data steward might define the standards for how customer addresses are stored to ensure consistency for marketing campaigns and reporting across different systems. It's about the usability and quality of the data for business.
Okay. And one more, the data subject.
Ah, yes, the data subject. That's simply the individual to whom personal data relates.
So, us, regular people.
Exactly. If an organization collects and holds your personal details, your name, address, medical history, purchase preferences, then you are the data subject. Understanding these distinct roles helps delineate responsibilities clearly, making sure no critical aspect of data protection is overlooked, and that accountability is always traceable.
Okay, so data isn't static. We know it constantly moves and changes throughout its existence within an organization. How does understanding this life cycle of data help us protect it, especially when it's in a dynamic cloud environment? It seems like a very logical way to approach security planning.
Thinking about data from a lifecycle perspective is a brilliant and systematic way to identify precisely where and when specific security controls are needed.
Okay.
The Cloud Security Alliance, which is a leading voice in cloud security, outlines 6 key phases. Comprehending each one is absolutely essential.
6 phases. Let's walk through them.
The first phase is create and update. This is where new data is generated, maybe a new customer signing up, a sensor collecting environmental readings, an employee drafting a confidential document.
Or changing existing data.
Right. It also includes updating existing data. Now, the absolutely crucial point here is that as soon as data is created or updated, it must be properly classified.
Classify it right away. Why is that so critical?
Because this classification isn't just some administrative step. It's the foundational decision that immediately dictates the required security controls for all the subsequent phases of that data's life. If you miss this step or get it wrong, you risk applying insufficient controls to sensitive data right from the very beginning.
Okay, so classification happens at creation update. What's next?
Next, almost simultaneously with creation, data moves to the store phase. This is when data is committed to a repository, whether that's a database, an object storage bucket, or a file system.
Where it lives.
Where it lives. And here, considerations like encryption at rest, redundancy across multiple locations, scalability to handle growing volumes, and ensuring high availability are paramount. You need to keep the data secure and reliably accessible while it's being stored.
Okay, store. Then.
Following storage is the use phase. This is where data is actively processed, viewed, or utilized by applications or people.
The active part.
Right. Running analytics queries, displaying customer information on a screen, editing a document, and if any changes or modifications are made during this phase, the data naturally circles back to the create phase for that modification and potentially reclassification if its sensitivity changes.
Makes sense. It's a cycle.
Exactly. Then comes the share phase. Data is rarely isolated. It's frequently exchanged between different users, applications, or systems.
Sharing data around.
Yeah, this could be within your organization, across various cloud environments, or even with external partners like suppliers or customers. This phase demands very careful management of permissions and often requires sophisticated controls like information rights management, which we'll definitely dig into later.
Okay, because sharing increases risk.
Significantly. The risks of data leaking during sharing are quite high, so precise access and usage controls are paramount here.
Got it. What happens when data gets old?
Well, as data ages or is no longer in active operational use, it typically moves to the archive phase.
Archiving, long-term storage.
Exactly. This involves transitioning data from active, often high-cost storage to long-term, typically much cheaper, storage solutions. Archiving is done for various reasons, meeting legal or regulatory retention requirements, or maybe because the data might retain potential future business value for historical analysis or auditing.
So keep it cheap and out of the way.
Pretty much. And finally, when data is no longer needed at all and its retention period is expired, it enters the destroy phase.
The end of the line.
The end. Here, it's securely deleted or destroyed, using methods that prevent any recovery. This is critical not only for good data hygiene, but also for complying with stringent privacy regulations like GDPR and preventing sensitive information from falling into the wrong hands after its useful life is over. Each phase you see has unique security considerations, and that initial classification drives the controls needed throughout the entire lifecycle.
So once data is classified and we understand its journey through these lifecycle phases, what does all this mean for actually controlling access to that data? If classification drives the controls, how do we put that into practice in a granular, effective way?
Okay, so to properly control access, you need to systematically consider three critical dimensions. Think of it almost like a 3D matrix.
3 dimensions, okay.
First, the actors. These are those who or what wants to access the data. This could be a human user logging in, a specific software process running on a server, an automated script, or another interconnected system. Understanding the identity and purpose of each actor is fundamental.
Who wants access? Got it.
Second, the functions. These define what actions they can perform on the data. Can they merely view it? Can they modify it? Delete it outright? Maybe they can only print it, but not copy it. Can they create new data entries? Clearly defining these permissible actions for each actor is key to implementing granular control.
What they can do? Okay.
And third, the locations. This is about where the data is physically stored, which cloud region, which database, which storage bucket, and also where the actors are attempting to access it from.
Where the data is and where the user is.
Exactly. For instance, is the data located in a specific regulated region, and is the user trying to access it from an approved network segment or maybe an unsanctioned public internet connection?
Yeah.
Geographic and network contexts are incredibly important.
Okay. Actors, functions, locations. What then?
Right. Once you've meticulously mapped out these three elements, actors, functions, locations, you then identify what is technically possible across all these permutations. You basically list every potential action an actor could theoretically perform on the data from any given location.
Everything that could happen.
Everything that could happen. This creates a comprehensive landscape of all possibilities, both legitimate and potentially illegitimate. Then, based on your organization's security policy, its risk assessment, and most importantly, the data's classification, you decide what should be allowed.
Narrowing it down.
Exactly. This is where you restrict the technically possible actions down to only the explicitly permitted ones, adhering strictly to the principle of least privilege. Finally, robust security controls things like access control lists, ACLs, network segmentation rules, multi-factor authentication are meticulously implemented to enforce these permitted actions, preventing anything outside those defined boundaries. It's an iterative, systematic approach to ensuring granular and context-aware control over your valuable data.
Okay, I've heard about this idea of breaking data into tiny fragments and spreading it around for both security and resilience. It sounds quite clever. How exactly does data dispersion work in the cloud, and what are the trade-offs an organization needs to consider?
Data dispersion, yeah. It often leverages a technique called cryptographic bit splitting, and it's an incredibly ingenious way to enhance both security and resilience. That's especially important in distributed cloud environments.
Okay.
The core concept is deceptively simple, but really powerful. You take a complete piece of data, divide it into multiple smaller fragments or shares, and then you distribute these distinct fragments across various drives, storage locations, or even different cloud regions.
Scattering the pieces.
Scattering the pieces. The primary benefit for security is that it dramatically raises the bar for an attacker. An attacker would need to access all or maybe a specific threshold portion of these dispersed locations to successfully reconstruct the original data.
So getting just one piece is useless.
Pretty much useless on its own. If they only manage to compromise one or a few storage locations, the fragments they get are utterly meaningless. Imagine a critical business secret, maybe a new product design, split into 10 fragments and scattered across different cloud regions or even different providers.
Right.
An attacker might breach one or two, but those individual fragments, they're just digital gibberish unless they have enough others to piece the puzzle back together. This significantly reduces the risk of a single point of failure, leading to a complete data compromise.
Okay, that's the security benefit. What about resilience?
Well, for resilience, some data dispersion schemes are designed so that the original data can be reconstructed even if a portion of the fragments are lost or become unavailable, maybe due to a server outage or a hardware failure in one location.
Ah, like RAID for the cloud.
It's conceptually similar, yeah. Like how RAID systems stripe data across multiple disks to protect against individual drive failures. It provides fault tolerance.
But you mentioned trade-offs. What's the downside?
Well, there are definite trade-offs. While security and resilience are enhanced, this method adds a significant layer of complexity to your data management.
Complexity. Okay.
And this complexity becomes particularly pronounced when it comes to compliance. If data fragments are spread across different geographical jurisdictions, say some in Europe, some in Asia, some in the US, you could face a bewildering tangle of diverse legal and regulatory requirements.
Oh, right. Data residency laws.
Exactly. Each jurisdiction might have different data residency laws, privacy mandates, or data protection acts. It makes it far more complicated to ensure your dispersed data adheres to all applicable laws simultaneously. So yeah, it's a powerful technique, but it demands meticulous planning for both the technical implementation and the regulatory adherence.
In the cloud, data can move in so many directions,
Yeah.
constantly flowing between applications, users, different services. It's not static at all. Why is it so incredibly important for organizations to understand and map out these data flows? What happens if you don't?
Understanding and meticulously mapping your data flows is absolutely crucial for both meeting complex compliance obligations and, perhaps most critically, for minimizing the risk of devastating data breaches. Cloud environments, just by their nature, can make data movement incredibly complex. And they unfortunately often reduce an organization's inherent visibility into exactly where their data is, how it's traveling, and what security controls are applied at each point in that journey.
You lose track of it.
You can easily lose track.
Mm-hmm.
Consider a typical cloud scenario. Raw data might initially be ingested from an on-premises system, then moved to a cloud-based application for processing. From there, maybe it's transformed by another cloud service in a different geographical region for analytics. Finally, the processed data might be shared with a third-party partner via an API, or integrated into a public-facing dashboard.
Wow, that's a lot of hops.
Exactly. And without a clear, documented picture of this entire journey, it's remarkably easy to have significant blind spots. And these blind spots, they're prime targets for attackers and often lead to compliance violations because you simply can't prove you're protecting data adequately at every single stage.
So how do you map this?
This is precisely where data flow diagrams become an indispensable tool.
Diagrams.
They help you visualize, often quite literally, the precise pathways data takes as it moves in, out, and through your organization and its various cloud services. By investing the time to map out these journeys from creation all the way to destruction, you gain a much deeper, more comprehensive understanding of your overall data architecture and, frankly, your attack surface.
Seeing the whole picture.
Seeing the whole picture. This deep understanding then empowers you to accurately identify potential risks, those specific points where data could be exposed, mishandled, or fall outside compliance boundaries. It lets you pinpoint exactly where security controls are needed most, whether that's encryption in transit, strict access controls, or robust logging. And critically, these diagrams serve as concrete evidence for auditors and regulators, demonstrating that you have a comprehensive grasp of your data's dynamic journey and have implemented appropriate protections every step of the way.
So not mapping your data flows.
It's like trying to navigate a complex city without a map. You're bound to get lost and potentially run into trouble.
Okay, so now that we understand the data itself, its life cycle, its movement, where does it actually live in the cloud? What are the different ways data is stored, and what are the implications for security when choosing one storage option over another?
Right. This is where the practical application of data security truly begins. Cloud storage isn't just one thing. It comes in many diverse forms, each with its own characteristics, ideal use cases, and crucially distinct security implications.
Okay.
Let's start with what we call virtual constructs. This is where, as a cloud customer, you don't get direct access to any physical hardware, but rather abstract representations of storage.
Virtual storage. Makes sense.
First, there's volume storage, often known as block storage. This basically emulates a traditional hard drive or disk volume.
Like a virtual hard drive.
Yeah, exactly. It's a virtual hard drive that you attach to a virtual machine, and the operating system running on that VM then manages the file system on that volume, just as it would with a physical disk. This type of storage is ideal for applications that need high performance, low latency access, like databases, operating systems, or enterprise apps needing direct disk-like access.
Okay, security concerns there.
Security considerations include encrypting the volume at rest and, of course, carefully managing access to the virtual machine itself that it's attached to.
Got it. What else in virtual constructs?
Then we move to object storage. This is a much simpler, highly scalable storage model. Data is stored as individual objects in a flat namespace.
Objects, not files on a drive.
Right. Each object contains the data itself, some customizable metadata, data about the data, and a unique identifier. It's primarily accessed via APIs, not mounted like a traditional drive. Object storage is engineered for massive amounts of unstructured data think files for static websites, large backups, media files like images and videos, or vast data lakes.
Like Amazon S3 or Azure Blob Storage.
Exactly those. Its simplicity, immense scalability, and cost-effectiveness make it incredibly popular. From a security perspective, managing access permissions to these objects and the buckets they live in is absolutely paramount. Misconfigurations here are a common source of public data breaches.
Yeah, seen those headlines. Anything related?
Closely related are content delivery networks, or CDNs. These are globally distributed networks of servers, strategically placed closer to end users.
For faster loading.
Precisely. Their primary function is to cache web content, images, videos, static files from an origin server, which is often object storage, at these edge locations. When a user requests content, it's delivered from the nearest CDN server. This dramatically improves load times and reduces the load on your main application servers.
So they work with object storage.
Often, yes.
Yeah.
They act as an acceleration layer for delivering large, unstructured data. Security for CDNs focuses on ensuring the integrity of the cached content and protecting against DDoS attacks targeting the CDN itself.
Okay, those are the main virtual types. Are there others for specific uses?
Yes, beyond those foundational types, we have storage optimized for specific use cases. Long-term storage is designed for extreme durability and cost efficiency, prioritizing these over immediate access speed.
Like archives.
Exactly. This is where you put historical backups, deep archives, compliance data that needs to be retained for extended periods, maybe years or decades, but doesn't require frequent access. You tolerate slower retrieval times in exchange for significantly lower storage costs.
Makes sense. What's the opposite of that?
The complete opposite end of the spectrum is ephemeral storage. This is temporary storage that exists only for the duration of a session or a running virtual machine instance.
Temporary. So it disappears.
Yep. When that virtual machine is terminated or stopped, any data stored on ephemeral storage is irrevocably lost, gone. It's used for temporary processing data, cache files, other transient information that doesn't need to persist.
So definitely don't put sensitive stuff there.
Absolutely not. A key security point.
Yeah.
Never store sensitive, persistent data on ephemeral storage.
Okay. Any others?
Finally, there's raw disk storage. This model provides direct access to a physical disk volume attached to a VM or server, bypassing the hypervisor's file system management.
Direct physical access. In the cloud.
Well, direct logical access to a dedicated physical resource allocated to you. It's typically more expensive because it's a dedicated physical resource, but it offers the lowest level control and often the highest performance. This makes it suitable for highly specialized applications needing custom file systems or extremely high I/O, like certain high-performance databases. Each type serves a distinct purpose, and selecting the right one is crucial for balancing function, cost, and security. Hashtag data fragmentation and dispersion algorithms.
That's fascinating how data can be broken up and spread around. So how exactly does the cloud do that? Are there specific algorithms that handle this fragmentation and dispersion beyond just the general idea?
Yes, there are indeed some very clever and mathematically robust algorithms that specifically handle this fragmentation and dispersion, often referred to as bit splitting.
Okay, like what?
The first significant one is called secret sharing made short, or SSMS.
Got it.
This algorithm works by taking a single piece of sensitive data, could be a file, a crypto key, a password, and dividing it into multiple shares. These shares are then distributed across different cloud servers or storage systems.
Okay, splitting it up.
Right. But the truly ingenious part is that a predefined threshold of these shares is needed to reconstruct the original data.
A threshold, meaning you don't need all of them.
Exactly. If an attacker manages to compromise a few servers and get fewer than that threshold number of shares, they learn absolutely nothing useful about the original sensitive data. Each individual share on its own is just random noise.
Ah, clever.
Yeah. For example, if you split a secret into 5 shares with a threshold of 3, an attacker needs to collect at least 3 of those shares to recover the secret. This makes it exceptionally resilient against partial compromises and excellent for protecting highly sensitive data or master crypto keys. No single point of failure reveals the whole secret.
Very cool. What's the other algorithm you mentioned?
The second powerful algorithm is all-or-nothing transform with Reed-Solomon, or AONTRS.
AONTRS. Okay, that's a mouthful.
It is, but it combines 2 distinct yet complementary ideas to provide both exceptionally strong security and high resilience.
How so?
Well, the all-or-nothing transform part ensures that every fragment of the data is absolutely essential for its reconstruction. Lose even one fragment, and the whole data set becomes useless, can't be put back together. Makes it incredibly hard for an attacker to recover anything meaningful from a partial set.
Okay, so you need all the pieces for that part.
For the transform part, yes. Then, the Reed-Solomon coding adds sophisticated error correction capabilities.
Error correction, like for hard drive failures.
Exactly. This means that even if some fragments are legitimately lost or corrupted due to a server outage, a disaster hardware failure, the original data can still be accurately reconstructed using the remaining healthy fragment.
So it's secure and resilient.
Precisely. By combining these two mechanisms, AONTRS offers robust security against attackers trying to piece together partial data and high resilience against legitimate data loss or corruption. Makes it a very powerful and practical technique for cloud storage, especially for critical archives or frequently accessed resilient datasets. #tag storage controllers and protocols.
What about how these diverse storage devices and architectures actually communicate with the systems that need to access the data? Are there special protocols or interfaces designed for this beyond just the raw storage types themselves?
Yes, absolutely. The communication between a computer system and its storage devices is managed by storage controllers, could be hardware or software components. They act as the essential interface, ensuring efficient data flow.
Okay, controllers manage the flow.
Right. And to do this efficiently and reliably, they use specialized protocols. One widely adopted protocol is ISCSI, or Internet Small Computer Systems Interface.
ISCSI, heard of that.
This protocol allows you to transmit SCSI commands, which is the low-level language traditional hard drives understand over a standard TCP/IP network, typically Ethernet. Essentially, it lets you access remote storage devices as if they were locally attached disks.
So storage over the network.
Exactly. But a critical point with ISCSI, and one that's a common oversight, is that it does not support encryption inherently.
Oh, really? No built-in encryption?
No. So if you need to secure that data in motion, especially if it's traversing an unsecure network like the public internet, or even an internal network you don't fully trust, you must layer in other security protocols, like IPsec, to encrypt the traffic. Failure to do so can lead to significant vulnerabilities.
Good to know. What else is common?
Then there's fiber channel,
Yeah.
FCSI. This is a high-speed networking technology specifically designed for storage area networks, or SANs.
And fans.
Unlike ISCSI, which runs over general-purpose Ethernet, fiber channel typically requires dedicated hardware and cabling, often using fiber optic connections. It offers dedicated, lossless, and extremely high bandwidth communication for storage traffic.
So super fast but specialized.
Exactly. Makes it incredibly fast and reliable, ideal for environments demanding the utmost performance and lowest latency, like large enterprise databases or big virtualization setups. The trade-off, though, is it's generally more expensive and complex to implement and manage.
Right. Specialized means pricey. Is there a middle ground?
There's a hybrid approach that tries to combine the benefits, FCOE, or fiber channel over Ethernet.
Okay, FCOE.
This protocol encapsulates fiber channel traffic within standard Ethernet frames. The big benefit here is it allows fiber channel traffic to run over your existing general-purpose Ethernet networks.
So you don't need the separate fiber channel switches.
Exactly. It helps organizations consolidate both their storage and networking infrastructure onto a single cabling and switching fabric. Can reduce the need for separate cabling and switches, potentially leading to cost savings and simpler management, while still delivering much of fiber channel's performance benefits. Each protocol serves different needs, really depends on the requirements. #tag storage clusters.
And what about combining multiple storage devices? For better performance, scalability, or reliability. That sounds like what people often call storage clusters. How do those work, and are there different kinds?
You're exactly right. A storage cluster is fundamentally a group of network storage devices or servers configured to work together as a unified solution.
Working together.
Yeah. Their primary goals are to significantly enhance data availability, scalability, and fault tolerance by distributing data and workloads across multiple nodes. This ensures that if one component fails, the others can take over, preventing service disruption.
Makes sense. Different types.
There are two main architectural types for these clusters. First, we have tightly coupled clusters.
Tightly coupled.
Okay. In this configuration, the nodes are very closely connected, often sharing memory or using extremely high-speed, dedicated interconnects. They operate almost as a single, highly synchronized system with very rapid communication and shared state.
So very fast communication between them.
Extremely fast. This tight integration provides exceptional performance and very low latency for data access. Crucial for applications super sensitive to delays like high transaction databases or real-time analytics platforms.
But probably expensive.
Generally, yes. The trade-off is they're usually more expensive to set up and maintain due to the specialized hardware and complex configuration needed for that close integration. Think of it like a finely tuned racing engine, amazing performance but needs precise, expensive upkeep.
Okay, what's the alternative?
In contrast, you have loosely coupled clusters. These consist of nodes that are more independent.
Loosely coupled, more independent.
Right. They communicate over a standard network, typically Ethernet, but with less frequent interaction and without sharing memory directly. This results in higher latency for communication between nodes compared to tightly coupled systems.
So slower communication, but what are the benefits?
Well, their major advantages are that they're often significantly more cost-effective to implement and manage. And critically, they're much easier to scale out. You can add more storage nodes more readily as your needs grow, often without the complex reconfigurations required in tightly coupled systems.
Easier to grow.
Much easier. They provide excellent scalability for distributed applications and large data sets where ultimate low latency isn't the single most critical factor. The choice between these two isn't just technical, it's strategic, based on performance needs, budget, and long-term scalability goals. #tag storage options by service model.
Does the type of cloud service model you choose, like SaaS, PaaS, or IaaS, actually impact which storage options you have available and, maybe more importantly, how much control you have over them? It feels like it would be a major differentiator.
Oh, it's a hugely significant differentiator. Absolutely. Your control over storage, and therefore your direct security responsibilities, varies wildly based on which cloud service model you're consuming. This is fundamental to the shared responsibility model in cloud.
Okay, let's start with SaaS, software as a service.
With SaaS, you, the customer, have virtually no direct access to or control over the underlying storage option.
None, really?
Pretty much none. You're essentially renting a fully managed application via a web interface. You interact with your data by uploading files, inputting info into forms, performing actions within the app itself. The cloud provider controls the back-end storage, completely handles all its intricacies, data placement, redundancy, backups, underlying security configs.
So your security responsibility is just
primarily limited to managing user access to the SaaS app, using strong authentication, and ensuring the data you input is clean and compliant. You don't get to choose the database type or the volume size. You just use the application.
Wait, that's SaaS. What about PaaS, platform as a service?
Moving to PaaS, you gain a significantly greater degree of control. If you're building a custom application, the PaaS environment gives you the framework and integrated services to do so.
So you're building on their platform.
Right. And this means you can define how your application stores data. You have options to select different types of storage, maybe structured storage for relational databases, unstructured for object storage, specific big data solutions. You decide the storage architecture for your application.
Like choosing between SQL or NoSQL.
Exactly. Whether it uses a NoSQL database or a relational one, how that data is indexed and queried. However, you still don't manage the underlying servers, the operating systems, or the physical infrastructure. The cloud provider handles those. Your security responsibility extends to configuring your application's data interactions and securing your application code itself.
More control than SaaS, but not full control.
Correct. Finally, infrastructure as a service, AIS, offers the most flexibility and consequently the greatest responsibility.
The building blocks.
The building blocks is a good way to put it. Here, you're essentially given virtual hardware VMs, virtual networks, virtual storage volumes. This means you have direct access to and extensive control over various storage types. Volume storage, object storage, raw storage, ephemeral storage.
So you can basically set it up how you want.
Pretty much. You have the freedom to deploy and manage virtually any database type, configure file systems, implement your own storage encryption solutions. In IS, you're essentially given the components of a data center in the cloud, and you decide precisely how your data resides and is managed. This provides extensive control, but also means you bear the lion's share of responsibility for configuration, patching, and securing your virtual environment, including all the storage.
Okay, even with all these sophisticated storage options and architectures available in the cloud, I imagine there are still significant threats that organizations need to be acutely aware of. What are the common risks to cloud data storage, and how might they actually play out?
You're absolutely right. Many traditional security threats are unfortunately exacerbated in the cloud due to its shared nature, and the shared responsibility model introduces some unique challenges too. Understanding these threats is definitely the first step in mitigating them.
So what's a major one?
One major concern is unauthorized usage. This occurs when cloud resources, including storage, are accessed or used without proper permission.
Using resources without permission? How?
Well, it could range from an attacker gaining access to your cloud account and provisioning expensive storage to host illegal content, to maybe internal employees misusing storage for personal files.
And the impact?
The consequences can be substantial, leading to unexpected cloud costs piling up rapidly, sometimes shockingly fast, and a degradation in performance for legitimate users, because resources are being consumed by unauthorized activities, maybe like cryptocurrency mining or hosting malware. It's a drain on resources and a potential legal liability.
Ouch. Okay, what else?
Then there's unauthorized access. This is perhaps the most common and often the most damaging threat. It's where sensitive data stored in the cloud is accessed by individuals or systems that lack the necessary permissions.
Getting access to the data itself?
Exactly. This can result in the exposure of sensitive customer data, critical intellectual property, confidential financial records. It can also lead to issues with data integrity, the data being modified or corrupted, or even complete deletion of important information.
And how does this usually happen?
Misconfigurations of access permissions, particularly in object storage buckets left publicly accessible, are an alarmingly common culprit here, frequently leading to high-profile public data breaches and massive reputational damage.
Right, the leaky bucket problem.
The leaky bucket problem, exactly. Regulatory noncompliance is another significant risk. Failure to meet the myriad of regulations and industry standards like GDPR or PCI DSS when storing data in the cloud. Well, that can lead to not only hefty fines, but also severe reputational damage and legal action.
Compliance is huge in the cloud.
Huge. Cloud storage solutions must meticulously adhere to specific data security, retention, and privacy controls mandated by these regulations. For instance, storing protected health information, PHI, in a cloud environment not certified for HIPAA compliance, or a financial institution failing to encrypt cardholder data at rest according to PCI DSS, can lead to severe penalties.
Okay. What about attacks like denial of service?
Denial of service, DDoS attacks, are also a persistent threat. Attackers aim to make data or systems unavailable to their intended legitimate users, thereby disrupting service continuity and business operations.
So stopping access.
Right. While often associated with network attacks, storage systems themselves can also be targeted by overwhelming them with requests, preventing legitimate access to critical data. This can lead to significant financial losses from lost sales, damage to brand reputation, and operational paralysis.
Okay. What about just losing data?
Yeah, theft or accidental loss encompasses a range of scenarios. Data can be accidentally deleted or logged due to human error, surprisingly common in complex cloud interfaces.
Oops, deleted the wrong thing.
Happens more than you'd think. It can also be lost due to underlying infrastructure failures on the provider side, though reputable providers have robust redundancy. And of course, data can be stolen if security measures, like strong authentication, access controls, or encryption, are inadequate or bypassed. This leads to direct data compromise and subsequent misuse.
And malware, still a problem in the cloud.
Malware remains a pervasive threat. Malicious software, including ransomware, viruses, spyware, can infect cloud storage environments.
How does it get in?
Often via insecure APIs, compromise user devices that then sync files with cloud storage, or stolen cloud credentials. Once in the cloud, malware can encrypt or corrupt vast amounts of data, leading to widespread data loss, significant downtime, and crippling ransom demands. It can paralyze an organization.
Ransomware in the cloud sounds terrifying.
It is. And finally, a critical, often overlooked threat is no sanitization. This refers to the critical lack of proper data removal or destruction when data is no longer needed, or when storage media is retired, repurposed, or fails.
Just deleting isn't enough.
Not nearly enough. If sensitive data isn't securely wiped or destroyed from disposed or failed media, it can potentially be recovered by unauthorized parties using forensic techniques.
Yeah.
Imagine hitting delete on an old database with customer records, thinking it's gone. Without proper sanitization, that sensitive data might just be sitting there, dormant, waiting for someone savvy to piece it back together.
Wow.
It's the digital equivalent of throwing out a safe with the keys still inside because you deleted the combination.
Yeah.
It's essential for you to understand and verify your cloud provider's data sanitization processes to ensure they meet your requirements, as you rarely have physical access to their media.
So beyond just how data is stored, what specific technologies and strategies do organizations deploy to secure the data itself? To make it unreadable or unusable to unauthorized parties, even if they somehow manage to get access to the raw bits.
Right, this is where we get into the clever techniques for data protection that go beyond just access controls or physical storage security. We're talking about techniques like data obfuscation techniques.
I've heard terms like masking and obfuscation used pretty interchangeably. What do these mean precisely, and how do they work to protect sensitive data, maybe without necessarily encrypting everything?
They are indeed often used interchangeably, yeah. And they both refer to a set of techniques designed to conceal or substitute sensitive data in a way that makes it unintelligible or unusable to unauthorized individuals, while still potentially allowing for certain operations or analyses.
Okay, so hiding or replacing data.
Exactly. Masking typically involves hiding all or part of sensitive data with placeholder characters. A common everyday example is when you see like 1234 on a receipt or an online form instead of your full credit card number.
Right, the asterisks.
Yeah, the asterisks. It's a preventative security control designed to prevent casual observation of sensitive data. Really useful for display purposes without needing to expose the full value.
Okay, that's simple masking. Are there other methods?
Oh yeah, several other methods of obfuscation. Random substitution replaces sensitive data with randomly generated characters or values that follow no discernible pattern related to the original data. Makes it very difficult, if not impossible, to reverse engineer the original value.
So just random junk, basically.
Random, but often format-preserving junk. For example, a real customer ID, CUST12345, might become XYZ98765, where the new value has no logical connection to the old one.
Okay, what else?
Algorithmic substitution replaces sensitive data with a value generated by a specific algorithm. The key here is that the algorithm maintains the original data's properties like its format, length, maybe even referential integrity across datasets without revealing the sensitive info itself.
Maintaining properties, how?
Well, for example, a date of birth might be shifted by a random number of days, but it still remains a valid date. This allows chronological analysis without revealing the exact birth date. The data still looks real and can be processed, but the sensitive core is hidden.
Clever. Keep going.
Shuffling involves rearranging sensitive data within a dataset to dissociate it from its original entities, while retaining the statistical distribution of the data points.
Shuffling. Like shuffling a deck of cards.
Kind of. Imagine a database of employee salaries. Shuffling them would mean all the salary figures are still present, but they're no longer linked to their original employee records. Prevents individual identification, but still allows aggregate statistical analysis of salary trend. Nulling or deleting characters is the simplest, just removing sensitive data or replacing it with nulls. Effective, but the data is gone, can't be used even masked. Varying numbers and dates uses an algorithm to change values systematically, maybe adding 5 to every date field or shifting numbers slightly. Got to be careful with this one, as original data might be recoverable if the algorithm is too simple.
Right.
And finally, replacing values with their hash, using a unique fixed length hash identifier instead of sensitive data. Famously used for passwords, you never store the password, just its hash. If the hash is compromised, the original password can't be easily reconstructed.
So these obfuscation techniques sound incredibly useful. Are they performed in the same way, or are there different approaches to how you actually apply them in systems?
There are two main approaches to applying these methods, statically or dynamically. The choice really depends heavily on the use case and the security requirements.
Static versus dynamic. Okay, tell me about static first.
Static obfuscation involves creating a separate, obfuscated copy of the data. This copy is then stored somewhere else, and the obfuscation remains persistent. The data is permanently altered in that copy.
A separate, safe copy.
Exactly. This approach is very commonly used to create a safe version of production data for use in non-production environments, like development, testing, QA, training. The idea is your developers, testers, trainers can work with realistic-looking data, same format, same integrity as production, but without ever touching or exposing actual sensitive customer or company info. Significantly reduces risk in less secure environments.
Makes perfect sense for testing. What about dynamic?
In contrast, dynamic obfuscation protects sensitive data by obfuscating it on the fly in real time as it's being accessed.
So the original data isn't changed?
Correct. The actual stored data remains unchanged and sensitive in the original database. However, when an unauthorized user or even an authorized user who doesn't need to see the raw data requests it, the system intercepts the request and presents only the masked or obfuscated version.
Can you give an example?
Sure, a classic real-world example is a call center agent's scream. When they pull up a customer's record, the customer's full credit card number or social security number is masked with asterisks right there on the agent's screen, even though the full sensitive number is securely stored in the back-end database.
Ah, okay. So it protects data in use.
Precisely. This method is incredibly useful for protecting data in use without altering the underlying stored data. Allows for granular control over what specific users see at any given moment. Particularly effective for operational security and compliance in live systems. Hashtag anonymization, de-identification.
Yeah. What about making data completely anonymous? That sounds incredibly important for privacy, especially with all the regulations like GDPR. How does anonymization work, and what are the complexities involved? It sounds tricky.
Anonymization, often called de-identification, is indeed a critical process for privacy and compliance. It involves removing or sufficiently obscuring personal identifiers from a dataset to prevent individuals from being identified from that data.
Okay, removing identifiers.
Right. The overarching goal is to transform or remove data points, so the information can still be used for valuable purposes like analysis, research, testing. But it can no longer be linked back to specific individuals, even when combined with other available information. Allows organizations to derive insights without compromising individual privacy.
But what counts as an identifier?
Well, the process has to carefully consider two distinct types of identifiers. Direct identifiers are pieces of information that, on their own, immediately and uniquely identify an individual. Think of obvious examples like social security numbers, full names, passport numbers, specific street addresses, unique biometric data. These are relatively straightforward to remove or mask during anonymization.
The obvious ones.
Right. The much greater challenge comes with indirect identifiers. These are pieces of information that, on their own, might not identify a person, but when combined with other data, they can be used to reveal an individual's identity through a process called re-identification.
Combining data points? Like what?
Common examples include demographic info like gender, exact birth date, even geographic indicators like a precise ZIP or postal code. If an attacker can gather enough indirect identifiers from various sources, they can potentially re-identify someone, even if direct identifiers have been removed.
Wow, really? Just from birth date and zip code?
Well, maybe not just those two, but if you know someone's birth date, gender, and the exact ZIP code they live in some less populated areas, that might be enough to uniquely identify them in a publicly available dataset.
That's scary.
It is. And that's why properly anonymizing data is a highly complex and crucial process, particularly for highly sensitive information like financial data, PII, and protected health information, PHI. If PHI, for instance, isn't properly anonymized for research, it could lead to significant compliance violations, like under HIPAA or GDPR, extremely costly fines, severe reputational damage. It requires a sophisticated understanding of data distribution and re-identification risks to achieve true anonymity. It's a delicate balance between data utility and individual privacy.
Okay, so if some data is so incredibly sensitive that we really don't want it anywhere near certain systems within our environment, maybe systems that aren't fully compliant, how does tokenization help us manage that risk and keep things secure?
Tokenization is an ingenious and powerful security solution designed exactly for that scenario for extremely sensitive information like credit card details, bank account numbers, even national ID numbers. The goal is to minimize their exposure across your systems and, importantly, reduce the scope of compliance audits.
Minimize exposure, reduce scope? How?
It essentially replaces that sensitive data with a unique, non-sensitive placeholder. We call that placeholder a token.
A token instead of the real data.
Exactly. Here's how it works in practice. The actual sensitive data is never stored directly in your less secure or non-compliant systems. Instead, it's sent to and stored securely in a separate, highly protected environment, often called a token vault or a secure data store.
A vault. Okay.
This vault is specifically designed with the highest levels of security, encryption, compliance control, perhaps adhering to stringent standards like PCI DSS for credit card info.
So the real data lives in the secure vault.
Right. When an application or system needs to process or store this sensitive data, but isn't compliant enough to hold the raw sensitive info itself, it initiates a request to the token vault. The vault then securely stores the real sensitive data within its fortified environment and, in return, issues and returns a random non-sensitive token, just a string of characters or numbers in place of the original data.
And the token itself isn't sensitive?
Nope. This token has no mathematical or logical relationship to the original sensitive data, making it meaningless if compromised on its own.
Can you walk through an example? Like e-commerce?
Sure. For example, an e-commerce platform taking customer payments. The customer enters their credit card number into a web form. Instead of the e-commerce app directly storing this card number in its own database, which would make the whole app fall under strict PCI DSS scope.
Right, big compliance headache.
Huge headache. Instead, it immediately sends the raw credit card number to a dedicated, secure tokenization service. This service, the Token Vault, stores the actual card number in its highly secure PCI DSS compliant database. It then returns a non-sensitive, randomly generated token back to the e-commerce platform.
And the e-commerce site stores the token?
Stores only the token in its customer database. Later, when a payment needs to be processed, the e-commerce platform sends this token to a trusted, compliant payment gateway or a secure internal app. This trusted application then uses the token to retrieve the actual card number from the secure vault for processing the payment with the bank.
So the sensitive data never touches the main e-commerce system.
Exactly. The highly sensitive card data never touches the less secure e-commerce application's main database.